So, composite beams. When we work composite beams problems, what is a composite beam? Concrete and steel. Concrete slab, steel girder. They're hooked together by Nelson studs, right? Okay? And there's two situations as a structural engineer that happen when it comes to design. The plastic neutral axis is either in the girder or in the deck, right? How do we decide where it's at? Sum the moments. That's exactly right. Really, you find this. You assume the neutral axis is right here at the interface between them. You sum the moments below. You sum the moments above. Okay. And what do you compare? What are you looking for? Which one's larger, right? It's not really summing the moments. It's summing the forces, the resultant forces. If the resultant forces are higher above this point, that means we have to move the neutral axis down. If the sum of the forces are larger below this point, that means we have to move the neutral axis up. All right? All right. And this math does it for you right here. It's doing the same thing. Okay? Of course, be careful. This is for a perfect, this is for in a very idealized case. You could easily add some craziness to it, and then you're going to have to go back to what's going on, what's happening. You can't not just use the equation every time. Sometimes you have to understand, actually all the time in this class you have to understand what the equation means and how it works. Okay, so say our life is easy and beautiful and this works out. And if this is the case and the plastic neutral axis is in the deck, and we use this circumstance, and this is the case, the plastic neutral axis is in the girder, and we use this circumstance. Okay? Okay. Great. Now, when it comes to studs failing, there's two ways a stud can fail. Stud can either fail in shear. What's the other way? Concrete can fail, right? We have some equations that we use to calculate that. This is basically the concrete failure. This is basically the stud failing in shear. Okay? Okay, great. We have some limits on maximum stud spacing. When it comes to design of studs, how do we do that? That's right. The load divided by the capacity of the stud. How do I get the load? It's from all the load in the concrete, right? All the load in the concrete. That's the short answer. Okay? Now, when you go and design those studs, you're going to get a certain number you need. Where do they go? That's actually only half the story when you do this, right? Because you're going to have to provide that same amount of studs on the left-hand side of that point and on the right-hand side of that point, right? Wherever that maximum moment is, right? Or wherever that point is that you're designing for the maximum amount of studs, okay? And those studs can be equally distributed. You don't have to have them clustered in certain areas, okay? Although, as you learn more and more, you will find that the studs at the end of the beam do much more than the studs in the middle. But since we're trying to minimize slip, okay, we just distribute them equally. Okay? Okay. Once you get to partial composite, you'll find that there's benefits of having studs at the end. Okay? Okay, great. So you distribute those studs equally from the point of maximum moment to the edge. Not necessarily from the center. From the point of maximum moment to the edge. So you may find out that you need 60 studs over here, and you're going to need 60 studs over here, something like that. Does that make sense? Okay. Awesome! We actually started to work a problem, which is so cool. So, in this problem, we're going to work a problem 3 times, with increasing complexity each time. And the first one is by far the simplest. So we have beams, we have them hooked together, we're going to make them composite. We figure out what our stud capacity is, we figure out where our plastic neutral axis is, we figure out that our design moment is 600 kip feet, and we're providing 858 kip feet. Ugh, gosh, that's awful looking. Okay. $810 kips divided by 15.9 kips per stud is 51 studs, and that's between the center and the end. Well, really, that should be between the max moment and the end. Okay? Awesome. Awesome. Now, at some point, you may want to figure out how I came up with 810 as the load here. It's an important point. And I'll say it right now. Maybe you'll go back and look at this. Since our plastic neutral axis was in the deck, I believe, let's see here, make sure that's correct. It was less than 1377 was less than, it's in the deck. Yes, it is. Plastic neutral axis is in the deck. It's somewhere up here. Then I could, if I wanted to, find out and plastify this. Okay, do all the equivalent stress block. That's one way to do it. Or, since the entire girder is plastified, I can just take the area of steel of the girder and multiply the Fy of that. Okay? That works in this case. It does not work if the plastic neutral axis is below. If the plastic neutral axis is below, we're going to have to plastify the deck. Not that hard, pretty easy to do, but it's what needs to be done. Okay? Okay, it's an important point to understand that what Isabella said earlier is exactly right. The studs you have to design for the load that's in the deck. Okay? In this case, it was easy to find because it matched the load in the steel. In cases where the plastic neutral axis moves down, it's not so easy, and you have to actually do the Whitney stress block for the deck. Not that hard. That's what you have to do. You have to, in a sense, solve for this resultant. Okay? And that resultant is what you have to provide. To design the studs. To design the studs. That's exactly right. Okay, so then I took 810 divided by 15.9. I got 50.9, rounded up to 51, and that's what I need between my max moment and my end. Okay? Okay, great. Now, these are some crazy, crazy useful equations. Okay? Crazy useful. Approximations for steel beam selection. So, if I'm doing a composite girder that has no limit on the beam depth, I can make my beam, this beam, as deep as I want to. Okay, it doesn't happen much in life. Oftentimes some architect doesn't want it to be too deep. Oftentimes some hydrologist, if you're doing a bridge, has like a 40-year flood or a 100-year floodplain. They don't want the bottom chord to intersect the 100-year floodplain. Okay, so you're constrained on the depth, or you have trucks that have to drive underneath it, so you're constrained on your depth. But if you're so lucky, you put your maximum moment in, and it's amazing how accurate this equation is. Put your maximum moment in kip inches, put your Fy in KSI, you put your phi factor in, which I believe is 0.85 in this case, and it will tell you your Z required, and we're going to show you how this works coming up. It's pretty awesome. If the depth is limited, then the area of steel you have to provide is a good estimate of it. Not saying it's accurate every time, but it's a good first estimate. Is 2 times the maximum moment, again in kip inches, divided by phi Fy d, which is the depth of the girder, T sub s, which is the thickness of the slab. Okay? Make sense? Okay, that's cool. Let's see this stuff in action. Now previously, I chose a W24 by 55. And let's just see if it's the most effective section. Let's say we want to push things. Okay? And let's assume there's no depth limit. So if that's the case, I would take 600 kip feet, change it over to kip inches, divide by phi 1.8, and my Fy is 50 ksi. I get a Z of 94.1 inches cubed. So I go and look that up in my steel manual, in my Z table. I find that a W24 by 44 is going to work. Do I need to worry about L sub B on composite girders? Why not? Compression blocks at the top. That's right. But we learned about L sub B. L sub B is the unbraced length, right? And you are 100% right in the previous girder. In the previous girder, you're 100% right. We don't have to worry about L sub B because we're always in compression, right? This problem, though, we don't necessarily know that that's where we're at this point, right? So in a sense, we're assuming that L sub B is not an issue. Okay, we're going to have to figure that out when it comes up later on. Okay. Also, if we have a continuous girder, where you could have, which we didn't, but if you have a continuous girder where you could have negative moments, then yeah, you better be careful. And you may end up using that case 2 or that case 3 of that C sub B calculations that we talked about in the past to work the problem. This is a perfect way. I mean, we think of the deck as bracing the top flange, right? And the bottom flange is only braced in a certain couple locations, all right? But right now, we'll go ahead and assume that there is no L sub B. Okay, so we're just looking at plastic moment. So we get all this information from the steel manual. Take my ASFY. I still have my plastic neutral axis. I do my same calculation. I get 1377. My plastic neutral axis is still in the deck, so that was a good assumption. Okay, it's a good assumption. No problems. I go ahead and solve for my A. I go ahead and solve for my moment capacity. I get 634 kip feet, and look at this, 634 greater than 600. It worked. The equation worked. Think I'm going to show you an example where it didn't work? No. But it works a lot. Like, I haven't found any way to break it yet. Okay? And this equation wasn't just made up, okay? It was derived. And we'll talk about how it was derived coming up once we get to plate girders. But what I want you to realize is that with that other section, we provided 858 kip feet. 858 kip feet. Way more than we actually needed. And with this equation, we're able to provide 634. I mean, that's like 5% more capacity than what we needed. That's awesome. That's awesome. And composite girders are a little tough to decide. How much does my deck give us? Okay? But for typical sizes in buildings, and actually this works for bridges as well, up to about 8 inches thick a deck, this technique works really, really nicely. Okay? Start to get things that are much larger than that, it starts to break down. Okay? But it works real nice. And that's what we want. We want simple things to get us in the ballpark. We did that real quick. We picked a girder real quick. And what do? We checked everything. Okay? What if it didn't work? Well, we changed the size of the girder. Right? Right? Okay, great. Stud design. Well, it's kind of interesting. We actually need less studs in this case. Which is kind of interesting. It's because we're not really designing for what we need. We're designing for a stiffness. Okay? So as the girder gets smaller, it's going to only be able to put, it can't put as much load on the deck. Okay? Okay. So we do our stud, our stud design again, 650 kips divided by 15.9 kips per stud. We need 40.9 studs, or 41 studs per side between the, again, where the maximum moment is. So I went ahead and did our stud spacing here. If our girder is 40 foot in length, dividing by 2 sides, dividing by 41, and I'm putting 2 studs at each spot. Okay, put them side by side. Okay, that means I can get away with 11.7 inch maximum spacing. Okay, so I prefer to go ahead and use 12 inches. And people will say, whoa, you calculated that you needed 11.7. 12 is more than 11.7. That's not conservative. Yeah, but it's like 0.3 of an inch, okay? I'm not going to lose any sleep over 0.3 of an inch, especially when I know that this whole thing's made up anyway, and the only thing we're doing is trying to not cause slip, okay? Does that make sense? So I'm going to use 12 inches. So we do our maximum spacing check. It's 34 inches. The maximum stud diameter is 1 1/8, and we got 3/4. Make sense? Awesome. So now let's work the problem the other way. Oh, no. I take that back. I guess I'm going to do live load deflection checks first, because it's not totally straightforward in how to do that with these things. You should know how to do it, but you probably haven't done it in a while. So we're gonna hold L over 360 as our live load deflection limit. We're gonna find 1.33 inches as that limit. And I go, well, for fun, you don't have to do this. You don't have to do it this way, okay? I mean, you don't have to do these steps. But I did this for instructional purposes, okay? I go, let's just look at if we only have the beam. Only have the beam, no deck. Okay? Just for instructional purposes. We're going to find out that from our live load deflection, remember I'm using the unfactored live load. And I'm going to assume that it's from distributed load. Okay? Okay. If it's not, then I'd use that loading, right, to find the deflection from that loading. But I'm going to assume it's a distributed load. It's just an assumption. Hopefully one would give you more information if you're going to actually work the problem this way. Okay, this is just the way I did it. And I'm going to back solve, let's see, so I guess that's the deflection that goes along with the distributed load. And I'm going to start plugging in for some of these things I know. This 8MLL, I just recombobulated this around a little bit, and I get 5 over 48 ML squared over EI is what this simplifies to if I plug in this information for my WL squared over 8, basically in here. My deflection, which I plug in all my constants, comes out to be 3.53 inches. If this doesn't make any sense to you, just think of back solving for WL. Back solving for WL and plugging into that equation. That's all I'm doing. No difference. Okay? So when I plug in all these numbers for my girder that I'm dealing with, I get 3.53 inches, which is greater than 1.33. It won't work. Have to take the deck into account. Look, I'm just doing this to show you that look how much deflection you get out of this system if you just have a girder. A bunch, right? A bunch. So, to actually do this calculation correctly, we need to transform the deck into an equivalent steel cover plate. This is using the modular ratio. You did this in strength and materials. It's probably just been a long time ago. Okay? So you got to find the modular ratio. The ratio of the modulus of steel over the modulus of concrete. So I find my modulus of my concrete, divide by my modulus of steel, and I get 9.3. I shrink the concrete cover plate, okay, to an equivalent width, basically transforming everything to steel, okay? The other way around, I could transform everything down here to concrete, but I wouldn't recommend doing it that way, okay? Now that I've got my new width and I have the same depth, that's important. The depth is the same. The depth is the same. When you do the transformation, you're only changing the width. If this doesn't make sense to you, look it up in your Strength and Materials book. Find my equivalent, my new centroid, 20.6 inches from the bottom of the beam. I find my I transform mode of inertia, the equivalent mode of inertia. I get 26.37 inches to the fourth. So all I did here was instead of going back and calculating all this stuff before, I just ratioed it. Took my old deflection, I ratioed my old I by my new I. If you don't like this, you can redo this entire calculation using the correct I. If we notice, everything in here is a constant. Constant, 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 constant. That's what's different. Okay? I'm just ratioing them. Saving myself doing math. And I get 1.13 inches, which is okay. Now please realize, you don't have to do this if you don't want to. Okay? This is done more for illustration purposes. To show that, oh my gosh, we don't get near the stiffness out of just the girder as we do with slapping this deck on top. Get a lot more stiffness. You get a lot more I. Look at this. It's way more, right? It's 4 times. It's 4 times as much, right? So you get 1/4 of deflection. That's cool. So, let's say we work the problem again. This time we're going to limit the depth to 16 inches. So the girder can be 16 inches below the deck. Again, that happens to you all the time. People will do that to you. So you say, okay, 2 times MU, change it over to kip inches. My feet factor is 0.85. Here's my Fy. There's my depth plus my 4.5. My area, 16.5 inches squared. Okay? 16.5 inches squared. Okay, so I'm going to do my same thing. Compare my ASFY versus my 0.85 F prime C. T sub S be effective. Again, I find my plastic neutral axis is in the deck. Guess what? When it comes to your homework, it won't be. Okay? And it's not that hard, but instead of using this canned equation, all you'll have to do is draw the cross-section, find out where that point of equal area is, plastify everything above, plastify everything below, find the resultants, sum the moments about the neutral axis. That's what you're going to do on your homework that's due on Tuesday. Okay? Great. If we get our A, plug into our canned equation, we get 675 kip feet, which is pretty awesome, man. 10% over design. That's awesome. That's really good. Just considering that I got there with a 1-line calculation. Okay? Now it's so sad, though, when I check deflection, which I'm not going to show you, I skipped some steps, but this 16 by 57 doesn't work. The deflection is 1.42 instead of 1.33. Fails my deflection limit. Okay? So that means you have to upsize. So let's realize that when we do these calculations, we do this simplified calculation, that's only for stress. Okay? That's only a strength check. And even though we do it, we cannot assume that that is going to provide the right answer. We have to check it. Okay? But we're going in with a very, very good guess. And that's what you want for design purposes. Start out with a very, very good guess. Okay? And it actually worked for strength. But when it came for deflection, it didn't work. and we needed to increase the size a little bit. So from a W 16 by 57 to a W 16 by 67. Ended up working. 10 more pounds. Oh no. Any questions? Okay, so with this last 5 minutes, I will start talking about plate girders. You guys got this, right? Last time? Yes? Okay. Yep. Anybody else need one? Take them back to the phone. Started talking about plate girders. Plate girders are beams that are composed of different plate elements that are combined in a more efficient arrangement than is possible with rolled shapes. Let me say this. If you can do something with a rolled shape, do it every day of the week. The only time you should ever use a plate girder is if a rolled shape doesn't exist or is extremely uneconomical, which doesn't happen very often. But in very deep girders, okay, extremely deep girders, plate girders become more advantageous. And I'll talk about why coming up. Okay? Almost always a rolled shape is more efficient than a plate girder. You will get people that will try to tell you that they're not, but they're not looking at all of the costs involved. Okay? Okay. Typically, they're used in extremely long span applications. Modern plate girders are welded, all welded together. If you look in books, if you look in throughout history, they've had riveted plate girders. Okay, we're not going to do that because in this country we don't build things that way. Okay, or you can use a bolted plate girder. In this country, we don't build things that way. Labor is way too expensive in this country to do something like that. Okay? Okay. The idea is to optimize the steel plate thickness to match the expected loads on the structure. Sometimes people also have yield stresses that are changing as well. What's that called? Do you remember? Hybrid girders. Typical span lengths. Okay, if you get to something like a 70-foot to a 150-foot span, deflection is going to control. Plate girders are usually the way that you go. Okay, it starts to get real hard to do 70-foot span with the rolled section. It can be done, but it gets hard, especially if you have depth restrictions. Okay, things like that. A 3-span continuous. Okay. Usually you have something like the first span maybe 100, the last span maybe 100, the middle spans are in the realm of 300 and some change. Okay, they do this on purpose to balance deflection, because as you push, as the bottom goes down, as the middle goes down, the ends go up. So we're talking about a continuous girder. Okay, obviously you wouldn't ship a 500-foot long girder out to the site. It would have splices in them. Okay? They may come in shippable sections. Okay? This may be 2 sections, this may be 2 sections, this may be 3 sections. Okay? Okay. Sometimes when you get really shallow, you have to go to tub girder type shapes. There's your plate girders. Okay? And look at that bottom flange. Look how that thick bottom flange you can put on there, how wide it is. Okay? Now, we've been building up into this point, talking about all of these different snail charts. Oh my gosh, it's ugly. All these different snail charts And here's 3 of them. This is the one for lateral torsional buckling, the one we've talked about since we were undergrads. Okay? This is the one for local buckling in the flange. A lot of details there. Gamma P, gamma R. This is the one for local web buckling. Gamma P, gamma R. We've talked about the gammas as B sub F over T sub F and H over T sub W. Talked about these previously. We've introduced these. We're going to actually be able to start using them coming up. Okay? Because we're going to start optimizing these things. We're going to start pushing the limits. Okay? We're going to start pushing them to a degree where all of a sudden local flange buckling may start controlling the moment. We don't care. All we care about is strength. Okay? We don't care what the controlling mechanism is. We just care about getting enough strength in there. Okay? So we're going to start playing with these. We're going to have one more that we're going to introduce coming up. Okay, coming up about more local flange buckling or local web buckling that's going to affect the shear capacity. So there will be 4 Snell charts, but right now we only have 3 of them. Does that make sense?